Hello, everyone. My name is Laura Prieto, and today we're going to talk about correlations in adaptive physical activity research, or APA research. As I said, my name is Laura Prieto. I'm a PhD candidate at the University of Wisconsin-Madison. I study kinesiology with a motor control and behavior focus. I also currently run a physical activity and motor skill intervention with Dr. Luis Columna that looks at the relationship between child motor skills and parent motor skills, as well as their ability to teach those motor skills to their children. So I'm really interested in the relationship between parent and child behaviors. A couple objectives for the presentation today. We're going to define the purpose of a Pearson correlation, interpret a correlational analysis, explore the application of correlational analysis in APA, and introduce similar statistical tests that you may see when you're reading research or when you're trying to answer your own research questions. So the focus of this presentation will be on the Pearson correlation. Some other correlation that you may see is a Spearman correlation. We won't go into detail about that, but we will define the differences between the two, as well as the differences between linear regression, which you may also see as you're reading and answering your own research questions. I will use examples from my own research, as well as talk about next steps for analysis. So starting off, I want to first talk about the differences between correlational analysis and linear regressions. So correlational analysis is purely descriptive. So I'm not trying to predict or design any specific experiments. In fact, I'm just trying to look at the relationship between two variables. The way I do that is using R, and R really helps me explain the strength as well as the direction of this relationship. In linear regressions, we also have other types of values that we're looking at, such as R, R squared, and R squared adjusted, which really relies on the number of variables you have. So correlational analysis is going to have paired variables, which is looking at two main variables. Whereas linear regression, you're going to have 2, 3, or more. And as well as in correlational analysis, there's no differentiation between the variables. So if I'm looking at parent motor skills and child motor skills, I can say parent motor skills have this relationship to child motor skills, or child motor skills have this relationship to parent motor skills. It doesn't matter. But when I'm doing linear regression, I am focusing on one dependent variable and looking at more than one independent variable. Correlation analysis also assumes a linear relationship between the two variables, but it does not make it explicit. So I'm not trying to predict anything with any formulas. And finally, correlational analysis does not address cause and effect, while linear regression really does try to predict or show that some variable is related in this way to another variable. So that brings us to one of the big points around correlation. Correlation does not mean causation. On the one side of this PowerPoint, I have an image of a scatter plot. The x-axis says ice cream sales, and my y-axis says crime rate. There appears to be a linear relationship, which would indicate that ice cream sales, as they go up, crime rates also go up. So these two variables, ice cream sales and crime rates, are related. However, we cannot make the assumption here that ice cream sales cause an increase in crime. So just because two variables are related does not mean they cause one another. This is something to keep in mind, especially as you're reading, that correlation does not mean causation. So what is correlation? Correlation is the association or relationship between two variables. That a correlational analysis can tell us the strength or magnitude of that relationship, and can also tell us the direction, whether that be positive or negative, and why. So it's really used to describe the relationship. And we have the Pearson correlation, which focuses on the relationship between two continuous variables. So you can think of something that has values from 0 on. So fundamental raw scores from using the test of gross motor development would be an example. And then we also have the Spearman correlation. And these are two rank ordered variables or different variables that convert scores, like we talked about raw motor skill scores, into ranks. So you would rank each participant. Now, I'm going to focus on Pearson. That's what I've used in my research. And that's usually what you see, especially when looking at continuous variables. And in a 30-minute presentation, I really want us to focus on that one idea. Now, how do we represent this correlation or this Pearson correlation? And this can also apply to different correlations, but we're going to really think about it through this lens. It's first a visual representation, so we use scatter plots to demonstrate that. Our summary statistic is the correlation coefficient, also known as R. And we also can look at statistical significance, which can be determined by a p-value. In this presentation, we won't go into depth on p-values. However, I do provide some references towards the middle of the presentation that can help further describe those definitions for you. All right, so the first idea about the visual representation is that scatter plot. So with the scatter plot, we're really looking that each participant or pair of participants has a data point. So for this example, our parent who scored a 6 has a child who scored a 3. So that this point right here would represent that pair of participants, and so on and so forth. When we're thinking about visual representation, we're also thinking about the strength of the association. So how related are these variables? And we really think about this about how far R is from 0, if we're looking just at the correlation coefficient. When we're looking at the visual representation, I like to look at how close all the points are to fitting on the line. So a perfect positive correlation, all of the points would fit perfectly on the line. A strong positive correlation, some points would fit on the line, but the distance from the line is going to be less than a moderate correlation here. So we're really looking at the distance of the points from this linear line. Visual representations can also tell us about the direction of association. So when we're looking at something that may have no correlation or no relationship to one another, we can't fit a line to it necessarily. So I imagine that as a flat line. Now, it can also tell us negative. Another word for negative correlations can be indirect correlations. So this tells us that as variable X increases, our variable Y decreases. And then it can also tell us perfect positive correlations or positive correlations in general. And there's another word for positive correlations is direct correlations. And in this example, we can see as X increases, Y also increases. So I mentioned briefly about the correlation coefficient. No worries, I do not, we're not going to be calculating any R here, but I do want to just mention what it is. So the correlation coefficient is the ratio between the covariance of the variables divided by the standard deviation of the variables. Now, for those that have taken a stats class or have yet to take it, you can start building connections here, especially at how this summary statistic is calculated. Now, R takes on a value from -1 to +1, which allows us to, how we was talking about last time, determine the direction of the association and also determine the strength of the association. So how do you interpret the magnitude or how big R is as an explanation of how strong the relationship is? One way of doing it is by a general interpretation based on general values. So these are values that researchers have developed, and it's a rule of thumb. It's one way of looking at it. Another way of looking at it is the coefficient of determination, which is also known as R squared. So we'll start first with the rule of thumb. This is the general interpretation, and this table is borrowed from Alkin's book, Statistics for People Who Think They Hate Statistics, which I thought I was that person, and I'm definitely not anymore. But it helps us describe the strength of the relationship between these two variables. And we see here that it gives us a range of 0.8 to 1 being very strong, so on and so forth. So this really helps us at least look quickly and categorize where we think the strength of this relationship is. Now, a more, I would say, rigorous way of looking at it is to use the coefficient determination, or R squared. And what that does, it tells us the percentage of variance in one variable that is accounted for by the variance of the other variable. So if I'm looking at how far away some points are from the line, I'm saying, oh, this other variable can help me account for that change or that randomness in this other variable that I'm seeing. I'm going to put this a little bit more simple. So an example is I'm training right now for a triathlon, and let's say I'm interested in two variables, running speed and the number of hours that I'm running per week. So let's say I plot a bunch of points and maybe I use other people on my run club. And what I find is that through all of this, I have an R or coefficient of 0.70. All right, so according to our last table, that would be a pretty strong relationship between running speed and the number of hours I run per week. Again, full caveat, this is completely made up. Now, if I use my R squared, so I square that value, then I get 0.49. What the coefficient of determination will tell me is how much of that variance is described by another variable. So the 0.49 would mean that 49% of the variance in running speed can be explained by the number of hours running per week. Or more simply put, that my running speed is related, 49% of what I think could influence my running speed is related to the amount of hours I'm running per week. So the stronger the correlation, the more variance that can be explained by the variable. Then when we're looking at R, we can also take a look at the direction of the association, whether that be a positive or direct correlation. So that would give us a positive sign here. This is example of R is 1, or a negative or indirect correlation, which can be identified by that negative sign right here. Something else to keep in mind is the statistical significance. So we can use a p-value to really tell us if the relationship between these two variables is statistically significant. You would have a null hypothesis, which in this case would be no relationship between two variables. The alternate hypothesis indicates that there is a relationship between the two variables. And then depending on your research question, your sample, you may determine a criterion. One that's very common is a p-value of usually less than 0.05, which tells us that 5% of this could be due to chance, which gives us pretty good confidence in saying that they are related. So I'm not going to go into detail with this, but I do want to bring into focus the idea that significance does not always mean that it is meaningful. So let's go back to my example about running speed. All right, so I did running speed and I did the amount of practice I had. But now I'm really interested in running speed and my leg length. So I sample a bunch of people. And let's say once I look at the correlation between running speed and leg length, I find that the correlation is 0.39. So it's my correlation coefficient. Now, if I'm taking a look at my table, 0.39 would put me at a weak to moderate relationship. All right. like not the worst. But once I do my R squared or use my coefficient of determination, I find that I have 15 or 0.15, which would give me 15% of my running speed is determined by my leg length or is influenced by my leg length. Even though, let's say that my p-value is still less than 0.05. So with all this information, I can really start thinking, is it really meaningful to be looking at leg length if only 15% of my running speed or variance of my running speed that I collected is due to this variable? And in this case, I would say no, even though it's significant, it may not be meaningful. And so these are some things to consider as you're interpreting these correlation coefficients, as well as thinking about how they apply to your own research. Okay, so here's a great application in fit families. Real life use of correlational analysis. We had a bunch of data from parents' motor skills. We had them do the test of gross motor development, which includes them, kicking, running, all those good things. We had their kids do the same exact thing. These were children with autism as well. So we had 43 children with ASD, about 7 years, give or take 2 years, and 43 parents, around 40 or give or take 6 years. We're looking at those fundamental motor skills, and we used a Pearson correlation, which we just went over in the previous slides. So the reason that we were able to use this is that our outcome or our variables were continuous. So bringing us back, Pearson is only used for 2 continuous variables. If they were rank order, they were ordinal, this would not be the test to use. All right, so we collected all this data, we looked at the relationship between them, and we're going to walk through my correlation coefficient, each of the different parts that we talked about, and we'll kind of bring you to the conclusion of it. So first, when we calculate the R or correlation coefficient, we got 0.14. The R is positive or gives us a direct possible relationship, indicating that parent locomotor skills increase, the child locomotor scores increase. Something to note here is let's really make sure we take a look at this scatter plot and what it looks like here. And then when we think about the strength of the relationship, R indicates a weak or no relationship as determined by that rule of thumb table. And then if we calculate R squared, or the coefficient of determination, approximately 2% of the variance of child locomotor skills is explained by parent locomotor scores. And our p-value was not less than 0.05. So with all of this information, we said there is no relationship between parent and child's locomotor scores. So in this study, we found that it didn't matter if the parent had great motor skills as measured by the TGMD, their child locomotor skills didn't seem to be related to that. Then when we look at ball skills, something that is more specialized, what we're thinking, there might be more of a relationship between these 2 variables. When we ran the analysis, we found that the correlation coefficient was negative 0.13, which indicates a negative or indirect relationship between the 2 variables. And the strength of relationship appears to be weak or no relationship at all due to the table, the rule of thumb table. And when we found the coefficient determination, we square that R. About 1.7% of the variance in child ball skills can be explained by parent ball skills. And our p-value is 0.40, which is not less than 0.05. So that indicates that there is not a statistically significant relationship between the variables. So again, with all of this information, we said that there was no relationship between parent and child ball skills. Again, our data tells us on some level that there's no relationship between the 2 of these. And I came in thinking that there may be a relationship between the two of them. So this really started us thinking like, okay, well, let's look at another component of the test of gross motor development. So then we looked at the gross motor index, which is that scaled standardized score. We run the R coefficient, and we find that it is negative 0.027. Okay, so this indicates that it is a negative, my bad, there should be negative, not positive, is a negative relationship indicating that as parent locomotor scores increase, child locomotor scores decrease. The strength of R indicates that there's no relationship between the two variables. And when I squared the R, it tells us that 0.07% of the variance of child GMI is explained by parent GMI. Finally, the p-value is 0.86, which indicates that there is no significant relationship between the variables. So surprise, surprise, what would we determine and conclude with all this? Again, there is no relationship between parent and child gross motor index. Yeah. Things you think you would make sense. Correlational analysis helps you really think about all the different factors that you're not measuring between these two different variables. At least these two variables are not related to one another. So this kind of blew it out of the water for me, right? I really thought there was going to be a relationship. So I went back to the research. A researcher, Dr. Koo, really looked at different parental behaviors and really suggested that that should be examined alongside parents' fundamental motor skills to identify if there's this lack of association that we observed in this analysis. What else could it be due to? Why is there no association between these two things? Also, we are looking at larger samples to really look about maybe who is the biggest influence on child motor skill development. And also thinking about having a sample of folks who do not have autism and then folks who have autism and how then maybe that relationship is the same or different. All the children in our study did experience motor delays. And so there's also some need to identify future research that could help identify strategies and also help us understand why maybe what is contributing to these motor delays and then what can help with future motor development. Okay, so all right, I apologize for that. We were just having a little technical difficulty, so we'll get right back at it. So then Dr. Q came up with this next study here, and he was really looking at the parental influences on parent-reported motor skills and young children with developmental disabilities. So he was looking at the pathway by which not just parent motor skills, but parent behaviors like support, explicit modeling, and PA are associated with motor skills. They had 135 parents of children with developmental disabilities, and they looked at all of these. Now, because there are multiple variables, we're not using a Pearson correlation anymore. So we're actually using a multiple linear regression, which we see here in his conceptual model, but also his correlation matrix towards the end. So Dr. Koo's idea was that children's PA led to children's motor skills, and parental tangible support and parental explicit modeling really influenced that PA participation. What they found was that, in fact, parental explicit modeling was related to our parental tangible support, and also parental reported child PA was also related to parental tangible support. So we're really looking at this idea of tangible support as something that really may influence that participation in children's PA, and also, but maybe not so much the motor skills themselves, as we see that these would be categorized as weak or no relationship between these variables. Here's another representation of this idea from Dr. Koo. And something that is what we see most often when we're looking at the relationship or correlation analysis. In this case, multiple linear regression, and the next step for our future research. So again, we defined the purpose of the Pearson correlation, we worked on interpreting it, and we also explored the application of correlational analysis in adaptive physical activity. Towards the end, we introduced multiple linear regression as something that you all can use and also interpret as you're reading. And I hope that this was a quick and application-focused explanation of correlational analysis. Thank you, and if you have any questions, please email me at my Wisconsin email. Have a wonderful day, y'all. Keep on being you.